Section 4.5, Undetermined Coefficients, Part 2. Let's begin with the superposition principle, which will expand our techniques for making appropriate guesses for the particular solution y sub p for an associated non-homogeneous problem, which is a continuation of the ideas that we looked at in the last section for undetermined coefficients. So the superposition principle simply says that if you have a function y1 which solves this differential equation with forcing function f1 of t, and if you have another solution y2 which solves this differential equation, notice the left-hand sides of the differential equations are identical, but the right-hand side, the forcing functions, are different. Then it turns out if you have one solution to this differential equation, another solution to this differential equation, not quite the same differential equation, but the same left-hand side, only the right-hand sides are different, then you can take any linear combination of y1 and y2, and it will solve the differential equation which has the linear combination of f1 and f2 on the right-hand side. So to see why this is true, and then we'll look at why it's very important and helpful to us, is first, if we just want to verify that this function is indeed a solution to this differential equation, we will do what we've been doing throughout the entire course. We will simply plug this in where we see a y, we'll simplify the left-hand side, we'll simplify the right-hand side, and see if we get a logically true statement. If we do, then this is in fact a solution. So we're just going to take this as our y. Everywhere we see a y here, we're going to put our c1y1 plus c2y2. We see here that there's nothing to do. Here we need to take the first derivative, so we just distribute the derivative, and we'll also distribute the multiplication of the b to get this. Here we need to take the second derivative, so we'll distribute the second derivatives. We'll also distribute the a, and we'll get these two terms. Now, if you notice, let's collect all of the terms that have a y1 in them. So here we have a acy1 double prime plus a bcy1 prime plus a c times c1 times y1. They're all the single underlined terms. And then let's group together all of the terms that have a y2 in them, and these are the double underlined terms. If we group them together like this, notice the single underlined terms all have a common factor of c1, so we'll factor it out. All of the double underlined terms have a common factor of c2, so we'll factor that out. And notice what's left behind here is ay1 double prime plus by1 prime plus cy1, which notice y1 was not a random function. It was a solution to this differential equation. And so that means when we put a y1 in here where we see a y, we know that this will equal f1 of t. So this must equal f1 of t. And similarly, y2 was not a random function. If you substitute a y2 into this, you will get a logically true statement. So that means when we substitute a y2 in here, we must get an f2 of t. So notice what we found. When you plug our y, which is c1y1 plus c2y2, into the original differential equation here, it simplifies to give us c1f1 plus c2f2. That means that in fact, this combination is a solution to this differential equation. Okay, how can that help us expand our techniques in the method of undetermined coefficients? Well, if we look back at a problem like y double prime plus 3y prime plus 2y equals this time, let's use a more complicated forcing function that's a combination of the types of forcing functions that we saw last time. It's an additive combination. Let's have a forcing function that looks like cosine t plus t squared minus 1. Now, if I were to erase this or cover up this term, we talked about how to handle a forcing function that looks like cosine t in the last lecture. We would just make a first guess of a cosine t plus b sine t. We would need to check for replication between that guess and the homogeneous solution, but that we would know how to proceed. Similarly, if I erase this and we only had a t squared minus 1, we talked about last time, if you have a second degree polynomial, you should guess a general second degree polynomial. So we would guess, if we've already used the letters a and b over here, then we would use something like ct squared plus dt plus e as our guess for this term. Of course, again, we would need to check if we have any replication between our form for yp and the homogeneous solution yh, but we would know how to proceed. Well, the superposition principle is actually saying that we can do both of these at the same time. Because if you think of this as your f1, if you think of this as your f2, then now we can just look at the F1 and we can make this part of our guess for YP based on the form of F1, and then we can make this part of the guess for the form of based on the form of F2. And we can do these all at one time. We don't have to do these separately. Now, as we said, you would need to check for replication between any part of this and any part of your YH solution. So why don't we go off to the side, look at the associated homogeneous problem, solve that very quickly using the characteristic equation, get our roots, notice that we're in case 1, and our general solution to the homogeneous problem would be C1 e to the minus 2t plus C2 e to the minus t, and now we just check. There's no replication or no linear dependence here with YH. There's none here, 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 or here. So all of this would be our guess. We do not need to revise our guess. So the upshot here is that the superposition principle allows us to deduce the correct form for sums and differences of familiar forcing functions or familiar forms. So it does expand our repertoire. Okay, our next task is before we've just been finding any one particular solution of the non-homogeneous problem, which we will again call equation N, but now we're going to be more ambitious. This time we want to find all solutions to the non-homogeneous problem, not just one solution, but we want to find them all. And we want to be able to write down a general form for the solution, for the form that all solutions to the non-homogeneous problem must take. Now, this is obviously a more complicated equation than the homogeneous equation we've been looking at, but we're going to see that building the general solution to this non-homogeneous problem is actually a two-step process, and we've already mastered each of those two steps. So here's how it goes. If you want to find the general solution to this non-homogeneous problem, we're going to first split off and look at the homogeneous version of this equation, which we'll call H. And then this is something that's familiar to us from section 4.2 and 4.3. We're going to go find the general solution to this associated homogeneous problem. And we know how this goes. You use the characteristic equation, AR squared plus BR plus C equals 0. You get the roots. Depending on what the roots are, you're either in case 1, case 2, or case 3. Case 1, case 2, case 3 dictates the look of the y1 and the y2 functions. But our YH is going to look like a C1Y1 plus a C2Y2, where we know how to find Y1 and Y2 based on which case we're in the characteristic equation. So this is all very familiar to us. We've done this. Okay, so let's get that general solution, call it YH, and just set it to the side. The second phase of this operation is now we want to return to the non-homogeneous equation, and this is what we've been doing in the last section, is now we just want to find any one particular solution, YP. And when I say find a YP, I don't mean just find its form. I mean you have to find the form along with the coefficients. So we need to get our hands on a concrete function YP that is a solution, any one solution, to this non-homogeneous problem. And we know that the form of YP, it depends on the form of F, but it also depends on the YH because it depends whether we have replication with YH or not. So this is a process we've done in 4.2 and 4.3. This is a process that we've done in 4.4 and will continue to do in this section. And so now the big theorem that we have is the following. Theorem: the general solution to the non-homogeneous differential equation is given by y of t is YH plus YP, where YH is the general solution to the homogeneous problem and YP is any particular solution to the non-homogeneous problem. So all we have to do is find our YH. We know that that's going to be a two-parameter family. We're going to find our YP and not just find the form. We have to actually find the concrete function YP. We add those two together, and that is guaranteed to be the general solution to our non-homogeneous problem. Let's take a look at an example. Let's find the general solution to the non-homogeneous problem y double prime minus y equals 2 minus t squared. Now this is where you have to be very careful, and when you're doing problems where they appear in the homework, an exam, or anywhere else, you need to make sure that you answer the question that was asked. You know, before we were just looking for any one particular solution to the non-homogeneous problem. But here they're asking for much more. They're asking for the general solution to the non-homogeneous problem. So based on the theorem that we just saw, we know that we need to go get our hands on YH. We know we need to leverage our knowledge from the last section in the method of undetermined coefficients to go find YP. Then we need to add those two together. So let's begin with that first phase. Let's look at the associated homogeneous problem. This is a second order, linear, homogeneous, constant coefficient equation, so we'll use the characteristic equation. The characteristic equation is r squared minus 1 equals 0, so the roots are r equals plus or minus 1, so we're in case 1. We can very quickly write down the general solution to the associated homogeneous problem, and its YH is C1 e to the t plus C2 e to the minus t. So we're done with that first phase. Now we turn our attention to the non-homogeneous problem, and we just have to find any one solution. We will use the method of undetermined coefficients. Looking at the form on our right-hand side, it looks like a quadratic function, so we will guess a general second-degree polynomial. I know that in order to find the coefficients, I need to plug this back into my differential equation, so that means I need to get my hands on the second derivative. I'll go ahead and pre-compute yp prime and yp double prime. I'll plug them back into my differential equation. When I do that, I get yp double prime, which is 2a, minus yp, which is this, and the parentheses are very important. On the right-hand side, I just get my forcing function, 2 minus t squared. So now this should feel familiar to us from the last section. We're just going to multiply this out, expand, and equate the coefficients of like terms. So if we just expand this out and gather up, we have our t squared terms, we have our t terms, we have our constant term. On the right-hand side, we have our t squared terms. We don't see a t term. It's there. It just has a coefficient of 0, and then we have our constant term. So I tried to color code these so we could see what's happening. If this second-degree polynomial on the left is equal to this second-degree polynomial on the right, then the coefficient of the squared terms must match. So minus a must equal a minus 1. We'll write that down. That tells us that a is 1. We see that the coefficient of the t term here must match the coefficient of the t term here in orange. So negative b must equal 0. That says that b is 0. And then the constant term here in green must equal the constant term here. So 2a minus c must equal 2. We'll write that down. If we rearrange, we already found a was 1, so we can rearrange this to solve for c, and we find that c is 0. So we return to our form. Our form was yp equals at squared plus bt plus c. But now, equipped with knowledge of what those coefficients are, we can plug in the a, the b, and the c, and we see that our yp actually has the actual value of our yp function is just t squared. Notice I'm not stopping with the form, I actually have to find the coefficients. So this is a particular solution to the non-homogeneous ODE. So let's make sure that we answer the question that was asked. We were trying to find the general solution to the non-homogeneous problem. So from our theorem, our y of t should be yh plus yp. Yh was c1 e to the t plus c2 e to the minus t. Our yp we just found from the method of undetermined coefficients was t squared. So we'll highlight this in yellow. This is our general solution to the non-homogeneous problem. It represents all possible solutions to that given differential equation. Next, let's consider the differential equation y double prime plus 3y prime plus 2y equals f of t. And let's practice getting the form that the general solution must take for each specified f of t. The idea here is that based on our last theorem, finding the YH is rather straightforward. The real work will be in finding the f of t, making sure that we check against replication with YH, and then also making sure that once we have the correct template for the form, we can execute the algebra to find the values of the coefficients. My teaching experience says that most of the time where the bottleneck for students in their learning is making sure they have the right form for the f of t, the form for the yp that's based on the f of t. So let's just practice doing that several times. So suppose we had this differential equation and we had an unspecified forcing function f of t, and let's just pick some different f of t's and see what the yp would look like. So if our f of t were 7 cosine 3t, Based on what we learned last time, our yp should be a full-blown sinusoid, a general sinusoid. It should look like a cosine 3t plus b sine t. Now we would need to check for replication in the homogeneous solution. So why don't we take the associated homogeneous equation and write it down? Let's go ahead and find this. I keep reusing this same left-hand side of the differential equation. So this is the same YH from the last example. But we can't know that this YP is correct without peeking at the YH. So let's look at our YP, let's look at our YH. There's no replication, there's no linear dependence, so this is our YP. So that would tell us that the form, I'm not saying that I've found the actual general solution, but the form of the general solution for the non-homogeneous problem would be YH plus YP. I know that this is the YH. This is the form of the YP. Sometimes in the homework, they ask you for the form. Sometimes they ask you for the actual solution. If they ask you for the form, you don't need to find the coefficients. If they ask you for the actual solution, you do need to find the coefficients. But that's just a matter of algebra and a little calculus. So this would be the form of YH plus YP. We would need to go find the A and the B. They are specific values for A and B that make this a YP, but this would be the form. Okay, let's practice. What if our f of t instead was e to the t plus 3? Well, if it's e to the t plus 3, notice this is a classic case of the superposition principle. This is two different forcing functions, an f1 and an f2, that are added together. The superposition principle says we have the freedom to just use our knowledge on each piece individually. So the e to the t, we should guess an a e to the t. For the 3, which is a constant, we should guess an arbitrary constant. Now we do need to peek and see if we have any replication or linear dependence with YH, so we're always looking back at the yellow. A e to the t is linearly independent from both of these. It's not a scalar multiple of either one, so this term is okay. And this constant is also okay. So there's no replication in YH, so that says the general form or the general solution to our non-homogeneous problem has the form YH plus YP. We know this is YH, and this is the form for YP. Again, if we needed to find the actual general solution, we'd have to find the values of A and B and substitute them in here. We're just concentrating on the form right now. What if our f of t looked like e to the minus 2t plus t? Well, based on the superposition principle again, because this is an additive combination of functions, I should just guess a e to the minus 2t here. I should guess a general first-degree polynomial function. It's very common for students to only guess bt here, but you have to guess bt plus c. And now we need to check for replication, so we look back up at our yellow. So looking here, we're looking at this compared to this, and we do see replication. This is a constant multiple of this. So there's replication right here. Notice this term is fine, no replication. This term is fine, no replication. But this term is replicating. This term is linearly dependent with a term in YH, so we must revise our guess. And remember what our theory says? Our theory says if you have a part of your YP that replicates something in YH, then you need to take that part of your YP and you need to multiply it by t. So I'm going to take just this. I don't need to multiply this. This is fine. Just multiply this by t. And now if you look at this, this is linearly independent from everything in YH. So this is our proper guess. And the general solution then of the non-homogeneous problem has the form YH plus YP, where the YH is above, and this is the form of your YP. All right. What if we had a multiplicative combination? So we had a 3t times an e to the minus t. Well, we kind of talked about these in the last section. For this part, we would guess an at plus b. For this part, we said we might be tempted to guess a c times e to the minus t, but that c doesn't really bring anything new to the table. So when we multiplied it out, we saw that we really only need 2 degrees of freedom. So this should be an at plus b times e to the minus t. We need to check for replication. I like to do this by just multiplying this out and then stare at these terms and stare at our YH and just see if you have any replication. Notice this term is fine because it has a t e to the minus t in it, but the other term is a constant times e to the minus t, and a constant times e to the minus t is sitting right here, and it is replicating. So the second term in our yp here is replicating something in our yh. So that's the part that needs to be revised. Okay, so what I'm going to do is, because this is multiplicative and not additive, this was my whole guess. So I'm going to take my entire guess and I'm going to multiply it by t. All right, because it was multiplicative when we started. I'm going to multiply this by t. And now when I multiply this by t and I were to break it apart again, you would see that both parts are linearly independent. So again, we're sticking with the theme that if you have a single term as your f of t, if any part of that term replicates yh, then you need to multiply your entire guess by t. Notice that's a different situation than when you have two individual terms at the outset. This is a superposition concept. This is not a superposition concept because it's a product rather than a sum. Okay, so we need to adjust. We'll take our original guess. We'll adjust by multiplying it by t. We checked and there's no replication here. So it turns out that this will work to find us a yp. Once again, our general solution to the non-homogeneous problem, it'll have the form yh plus yp for the yh that was above in yellow, and this needs to be our yp. You could either write it like this or like this, but this would be the form of our yp. Keep in mind, to actually find the yp, you would need to do the method of undetermined coefficients to nail down the values for a and b. So really the last thing that's left in this section is you may encounter problems that have initial conditions. So up until now, all of our questions that I posed as examples, there were no initial conditions present. We were just finding general solutions to the overall problem. If initial conditions are present, then our workflow has to be in a very specific order. So if initial conditions are given, and here's an example. So suppose you have y double prime minus y equals 2 minus t squared. So this is obviously a non-homogeneous problem. Second order, linear, non-homogeneous with constant coefficients. And we see that we have initial conditions. And I don't write down the instructions here other than to say solve. Well, you don't find a general solution to an initial value problem. You only find a specific function that solves all of this. So how do we go about doing this? Well, if initial conditions are given, you must find yh first. Then you find yp along with its coefficients. The form is not enough. You have to find it with its coefficients. Then you build the general solution to the non-homogeneous differential equation by making y as yh plus yp. This will be a two-parameter family. There should be no unknown constants in this because you've already nailed them down by finding the coefficients in the step above. And now you will have two unknowns, C1 and C2, and they are going to be, they're in Y, but they're in Y because they're sitting in YH, and they are determined from the two initial conditions. If you flip-flop the order here, you can get a bunch of nonsense, so you need to be very careful. Sometimes students go apply the initial conditions to the YH before they found their YP, and it just kind of goes off the rails. But what you need to do is you need to find your YH, you need to find your yp with its coefficients. You need to add those together to get the general solution to your non-homogeneous problem. And only when you have the general solution to your differential equation can you embark on applying the initial conditions to nail down the two parameters in that family. So that's perfectly consistent with everything that we've done so far. So don't deviate from that theme. Okay, I'm recycling this example, so the y here is yh plus yp. We found the yh above. We found the yp above. And so this is our yh plus yp. Now I will apply the first initial condition, y of 0 to this. I get c1 e to the 0 plus c2 e to the minus 0 plus 0 squared. And the initial condition is 1, so it must equal 1. If you stare at that, that gives me c1 plus c2 has to be 1. Just hold on for a second. That's one equation and two unknowns. Before I can apply the second initial condition, I have to find the derivative of y. So I'll just take the derivative of this. Then I'll apply the second initial condition. Y prime at 0 is c1 e to the 0 minus c2 e to the minus 0 plus 2 times 0. And the initial condition is 2, so I have to set that equal to a 2. When the algebraic dust settles here, this gives me a c1 minus c2 equals 2. Highlighted in green, we have two equations, two algebraic equations and two unknowns. To linear equations and two unknowns, so they're especially straightforward to solve. Solve them by your favorite technique, elimination, substitution, whatever you like. And we see that C1 is 3/2 and C2 is -1/2. Don't stop there. What we ought to get as the solution to the initial value problem, it ought to be a particular member of the general solution. So here's the general solution. We're trying to pull out one member from this family with particular values of C1 and C2. We've nailed down the C1 and the C2, so let's just substitute those in. C1 is 3/2, C2 is -1/2, and so this is the solution to the initial value problem. So in the homework, you're going to see that sometimes you have initial conditions, sometimes you don't. Sometimes you're asked to find the general solution to the non-homogeneous problem. Sometimes you're just asked to find a particular solution to the non-homogeneous problem. Sometimes you're asked for the form of YP. Sometimes you're asked for the actual function, concrete function for YP. So be sure that you pay attention to the question that is asked, but you ought to be able to do everything in the homework based on the examples that you've seen here.